Okay, so welcome to this class. We are going to give series of class that will be uploaded to YouTube. So if you are watching this in YouTube, be aware that there are other classes. This is a course, an introductory course in open quantum systems. So we will work basically with the most common approach, that is the Markovian approach. So we will discuss basically what is called the Redfield equation and the Lindblad equation. Okay, we will basically have two classes in deriving these equations, going through all the approximations and discussing this, and another class in just some practical rules on how to solve this kind of equation and how to work with them too. Okay, so in this first class, I will present the general problem in open quantum systems. Basically, it is, imagine that we have a quantum system that is very big, but we are interested only in a small subpart of this system. Okay, so this we are going to call, this will be the Hilbert space of our total system that we will call HT, and that we can divide in the Hilbert space of the system that I will not label it because it's the one we are interested in. Okay, with the direct product of what we call the environment. Okay, so the Hilbert space of the environment. Okay, so here we will have the Hilbert space of the system, and this will be the Hilbert space of our environment. Okay, the problem we are interested is in deriving the equations of motions for density matrices or for states that live in this Hilbert space. Okay, in general, what we are going to have is a Hamiltonian of the full dynamics of the full system plus environment, that we can decompose the Hamiltonian of the system plus the Hamiltonian of the environment plus what we are going to call the interaction Hamiltonian. Okay, so basically the dynamics here is controlled by one Hamiltonian. Here we will have the Hamiltonian of the environment, but we will also have, of course, some interaction between the system and the environment, because otherwise we will just work with our system and we don't need to go into open quantum systems. Okay, so here you can see that we have included this alpha, and this is very arbitrary because this you can also include in the interaction Hamiltonian. So the rule is that we separate the interaction, so this should have some eigenvalues that are comparable to the ones that we have in our system. Okay, and if they are bigger or smaller, we add this alpha to control it. Okay, so this will be what we call the interaction strength between the system and the environment. And you will see that the most important approximation we have to make is to make this very small. Okay, the total system will be described by a density matrix in general, that we will label as rho of T. Okay, that is, in general, it will be composed by the product of the density matrix of the system and the density matrix of the environment. Okay, where, of course, rho of T belongs to the operators in H of T, rho belongs to the operator in H, and rho of the environment belongs to the operator on H of the environment. Okay, the same for the Hamiltonian. Is it clear? Let me write in the Hamiltonian. H of S is an operator H of the system, we don't label it. H of the environment is an operator on H of the environment, and the interaction Hamiltonian belongs to the total. It's an operator in the total Hilbert space because it applies both to the system and the environment. Here I have, if we write it this way, you can think that the dimensions of the system, they don't match, okay, because we are adding this system Hamiltonian. Okay, this I have said, maybe I will make this several times. Okay, the one of the system we don't label. Okay, you can see because the dimension of the Hilbert space of the environment can be different of the dimension of the Hilbert space of the system, you could think that these are just matrices of different dimensions, okay? And this is because of the notation. Usually, these have to have the dimension of the total Hamiltonian, okay? This is because when we write here, we are saying that this is the Hamiltonian acting on the system multiplied by the identity by doing nothing into the environment, okay? And this will be the identity, okay? Let me write it properly. Identity in the environment plus the identity in the system times Hamiltonian in the environment, and then all the dimensions match, okay? Basically, this means that we are acting on the system, doing nothing in the environment, or acting in the environment, doing nothing in the system, okay? So usually these identity matrices, we don't write them down, okay? Because it's just a way of making the notation lighter, okay? But you have to be aware that when you are applying to one place or to another, okay? What do we want? I mean, the problem, if we describe like this, could be how to describe the dynamics of the system, okay? We can say, well, the total dynamics of the total system, it is very easy to calculate, or at least to know the equation that describes it, and this is the von Neumann equation, okay? If you have pure states, it will be Schrödinger equation. As in general, we work with mixed states, it may be the von Neumann equation, that is just the total system dynamics given by this equation. Bar H total for total of T. No, not yet. Okay? So now we can think, why don't we just solve the von Neumann equation? This is the only time I write H bar, okay? Because we are going to take this convention, so we don't need to write H bars all along, okay? Why don't we just solve von Neumann equation and we get our system? This is because in general, it could happen that the environment is very big, for instance, and it is very difficult to solve, okay? And we are only, our only point of interest is what happens in our system, not in the whole system. Imagine if you have an atom, the atom interacts with the magnetic field everywhere, but what you want to know is what happens to your atom, okay? So you don't need to calculate the whole dynamics, and this is something very common also in classical physics, so it's not only about quantum mechanics. The concept of bath in thermodynamics is I have a system, and I have another system that I assume that is very big, and so on, and I care only on my system, okay? So this is the problem we want. So basically what we want is to have a dynamical equation. So these are the requirements that we are going to impose in our equation. We will see that for the Redfield equation we will fulfill some of them, but not all of them. But for the Limblad equation, that requires more approximations and more assumptions, we will fulfill all of them. Basically, what we want is that we have a dynamical equation or equation of motion only for our system density matrix. Okay? So it's something like T dot should be some functional of rho of T. Okay? And we have to include, of course, it will depend on the environment degrees of freedom, because the environment is this, but the state of the environment should not appear explicitly here, okay? Otherwise, we will go back to the von Neumann equation. Second, this is this equation of motion. Let's write it as a reduced equation of motion. Okay, our second requirement is we want f of t to be depending on the state. So the derivative of our function should be dependent only on the state of our density matrix at the same time, more or less, okay, or around this time. Okay, this is that we are imposing Markovianity. Basically, what this means is that we don't want to be, if we are at a certain time and we want to calculate the dynamics of our system at this time, we don't want to integrate over all the previous dynamics of our system. Okay? So basically, if you give me the state of the system at a certain time, I can keep making the evolution without knowing where it comes from. So this is also more or less equivalent that we have to say that we have to forget the initial state of our system. Okay? And then more mathematical requirements. If we start with a density matrix, what we want is to keep having density matrices. Okay? So basically, for instance, the trace of rho of t, we want it to be equal to the trace of rho of 0. Why? Because density matrices, they have trace 1. So I don't want the trace to be changing over time, because otherwise I will lose the point of a density matrix. Okay? This is called trace preserving. Okay? So we want an equation only on the density matrix of the system, that is Markovian, that preserves the trace. But there is another requirement that we make into density matrices. And remember, density matrices, so this could be the fourth requirement. The other way around. Density matrices are positive metrics, positive matrices. Okay? That means we know that all the eigenvalues are real because they are also Hermitian, but we know it's not enough to impose that they are real. They have to be higher or equal than 0, okay? Because they represent probabilities. So if I start with a positive density matrix, that is what I should do, because it's a real density matrix, I require that for any t, it keeps being positive. So it keeps being a density matrix, okay? And this is called positivity. But even more, another condition is this density matrix can form part of a bigger system, as it does, because it's connected with the environment. So we are going to require that if I couple my density matrix back to the identity on any dimension, it should still be positive. So when I evolve it in time, this requirement should be still fulfilled. Okay? This is what we call complete positivity. Okay? And any equation that these are some things we want from our equation, but this is just to keep this thing. Of course, sorry, I have forgotten to mention that complete positivity implies positivity, for sure, but not the other way around. Okay? There are many maps, many equations that are positive, but not completely positive. Okay? And basically, these two is what we want to be able to solve our equation or our dynamics. Okay? These other three is just to preserve the physical state that we have. Okay? To preserve it to be physical. We will see that Redfield equation, that is the one we are deriving now, fulfills these three. Okay? So it is reduced, it is Markovian, and it is trace preserving, but not always positive. Also, of course, because this implies this. If it is not positive, it is also not completely positive. Okay? The Lindblad-Master equation, that is the one we derived in the second lecture, it is trace preserving and completely positive. Okay? So this is what we want. So I say we are not getting all of it today. We are getting only part of it, but let's do it. So what is our initial point? Always the von Neumann equation. Okay? The von Neumann equation First of all, we are going to change our picture. I'm going to divide in several steps. I don't remember how many, 4 or 5. Several steps. Okay. The first one is to change to the interaction picture. I think there are 4 steps. Some of them you will see much longer than the other. Okay. So first of all, we are going to change to the interaction picture, basically because all the more relevant information is in the interaction Hamiltonian. This is what we want to work with, and this we don't go into details because this you can see in any quantum mechanics books. I learned it in a quantum field theory book, Mandel and Schwann, 2 pages, and then it's very easy. Okay, basically in the interaction picture, what we are going to do is to separate. You know, there is the Schrödinger picture, that is the one we usually use. This is Schrödinger picture. The Schrödinger picture, the state of the system changes with time. The operators, they do not change with time. Okay? You can go to the Heisenberg picture, that is the other way around. The state of the system remains the same. Operators, they change with time. And you can prove very easily that they give the same results. Okay? Interaction picture is in the middle. Basically, all operators, and now we are not going to notate them with this hat, okay? That probably will forget all time long. Okay, you remind me, I put hat. Okay? In the interaction picture, operators, they change this way. So basically, we take half and half. Our system state is going to change only because of the interaction Hamiltonian, okay? And the system and environment Hamiltonians will modify my operators, okay? This is quite pretty standard, and in this interaction picture, the von Neumann equation reads something like this. Now, I hope you can see here because I don't want to write all the time derivative with time, and this is quite painful. Okay, so this is the time derivative, of course. So I write the hat and then the dot. Okay, if I switch them in a certain moment, it doesn't matter. Okay, it's still the same thing. Okay, then this will be we have something in this form. That is still the von Neumann equation. We haven't made any assumption, anything, okay? The only thing is, as we are now with the interaction Hamiltonian, we can take this alpha that is here, we can take it out, okay? But again, no assumption. This is just a matter of notation, okay? As we have only the interaction Hamiltonian, we can make explicit this alpha dependence that we are going to need in a moment. Okay, and this is exactly the same as here, exactly equally difficult, and so on. Okay, so we have done nothing important yet, and this is the one we are going to work with. And now we start doing things. Okay, step 2, we're going to expand it. So this equation we can solve in a very easy way. Okay. This is not mathematically very accurate, but the result it is. So imagine that we take this t. Since this is the only time I will write the derivative explicitly. Interaction of t hat rho t of t hat, okay? And one thing that physicists will like to do, if there is a mathematician watching, you can skip 1 minute into the future, okay? That is say, okay, this derivative we take as a fraction of differentials. I take this differential here, and then I integrate, okay? And mathematicians, they hate it because this is a derivative, it's not a fraction, blah, 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 blah. But at the end, you can, let's say, you take this there, hat differential of t. Okay, and now we integrate between 0 and t. Between 0 and t. Sorry. As we are integrating between 0 and t, this means I have to change here my variable, because this is the one I'm integrating. Okay? S, and here too. S. Okay? I can integrate in any numbers I want, so I choose between the initial state and the state, the point where I want to calculate the dynamics. Okay? So this means that rho t of t will be equal to rho t of 0 hat minus I alpha, this beautiful integral between 0 and t of h I of s rho t of s differential of s. Okay? This step here, mathematicians will cry if they see, but from here to here, it's safe. Okay? What we have done doesn't break any rule. So, nice, we can expand it, but this is also. Now we have the formal solution of our problem. So if we want to calculate at time t the total system, okay, we just need to calculate this integration. Okay, but this is a very difficult integration because the Hilbert space is very big, and also what we want at the end is to get a dynamical equation, not just the solution. Okay, so what we are going to do is to take this. This is why I have colors too. With the solution here, this specifically, and plug it here. Okay, so we make an expansion in our dynamical equation. Okay, not only the solution. Let's see if I do it with no mistakes. Rho t hat dot of t will be then equal to minus I alpha hi of t. Now this guy goes here, rho t 0 hat and hat, and now we have this multiplied by this. Yeah, is minus times minus plus I times I minus alpha squared integration between 0 and t of hi of t commutator of hi of s rho of s hat close differential of s. If I make any mistake, hi of t, then hi of s, rho, this is rho total. Okay, I think we are fine. Okay, if you spot any sign or something, you just tell me and we can correct it on the fly. Fair enough. Okay, we have made an expansion. Now we start cooking and we are going to make our first approximation. Okay, because here one thing that bothers is that this is a function of s. Why we don't like it? This means that the dynamics at time t will depend on the integration of the whole dynamics. Okay, this doesn't fulfill the first condition, that I want the dynamics of my system to depend only on the state of my system at this time, okay, or close by times. Okay, so this is highly non-Markovian. So if you want to calculate what is the derivative of your state, you need to know all the history of your state. Okay, what can we do? Let's apply the same trick again. This integration here, this one exactly, let's do again differential of rho t of s equal to integration of, let's call this s prime, not to get confused with this s. Okay, this is minus I alpha hi of s prime rho t of s prime differential of s prime. Okay, of course I can label this as s prime or whatever I want, because this is just an integration variable. The only thing that matters is the limits of the integration. Where do I integrate from? Okay? What I want is to get rid of this rho t of s. Okay? I want to transform it into rho t of t. So I don't have to integrate all the time or all the state. Okay? So I can choose, for instance, I want s and t and s. Okay? So I integrate between t and s. So I'm going back in time, but it doesn't matter because I can change it just adding a -1 sign. Okay? So I get that rho t of s will be equal to rho t of t minus I alpha, the integration between t and s of hi of s prime, rho t of s prime, differential of s prime. And what do we do now? The same as we have done before. We want to get rid of this, so we plug this into here. Okay? Now you can see why this step is called expansion. You expand in powers of alpha. Basically, now we are going to get that rho t. Sorry, this I have forgotten all the hats. Okay? Hat. Okay? So now we go back here, go from t of t minus I alpha hi of t rho t of 0. This part we haven't changed. Okay, we are doing nothing to this part. Minus alpha squared integration between 0 and t of hi of t commutator hi of s hat, and now here it comes this guy here, rho total of t commutator differential of s. Okay, and now this part goes here and get me a very big integration, double integration in s and in s prime with this commutator and this commutator. But why we do this is because we can see that this alpha square is going to be multiplied by this alpha here. Okay? Not at the beginning because this has no alpha, but when I include this part into here, it will be an alpha square, and this we can say that is of order alpha cube. Okay? Again, this order alpha cube is this integration where I plug this integration. This is super complicated. Super complicated. Okay? But we don't care if we don't take them into account. So the first approximation we're going to do, yellow, is that we have weak coupling between our system and our environment, meaning that this alpha is small. Okay? And if this alpha is small, we cut here. Smaller than 1. Okay? And this is the most basic approximation in open quantum system. Weak coupling. Okay? The Born approximation. There are two. The other one we are going to see in a moment. These are the most important. Can we make strong coupling dynamical equations? We can, but it's very difficult. You have to, at the beginning, what you have to do is to take more orders here. Okay? This is the Redfield approximation. The Redfield equation is a second order approximation. Okay? You take more. Let's say usually you cancel, then you get fourth order approximations, and so on and so forth. And everything becomes much more difficult. But there are many approaches that they can use. And going to a master equation that you can solve that is doable in high coupling, this is an open question, and many people is working on it because it's very interesting, because this weak coupling, it happens in many systems. For instance, an atom coupled to the radiation field is weak coupling. Many other things, like biology, for instance, to molecules that interact, is absolutely not weak coupling. Okay, so going beyond this will be very interesting, but not for this class. So let me go back and erase a little bit. So let's try to keep this. So start here. Okay, so now we have our equation that depends only on the state of the system at time t. But it is still have several problems, okay? So let me copy here the equation because we're going to start with it. Rho of t times t hat dot equal to minus I alpha h t so 0 total, correct? H interaction, of course, hat and hat minus alpha square integration between 0 and t of h interaction of t commutator of h interaction of s rho now of t commutator differential of s hat and hat and hat and everything has hats. Okay, I think it's correct. Okay, I did it by memory, so it's very well prepared. Okay, so because we have removed all the
first HI should be T or S?
The first one is T, the second one is S.
Okay.
Okay? Because this comes from the von Neumann equation, and this comes from the first interaction of the function. Okay? So it's okay. Problems with this equation, I mean, you can see that it's a very difficult equation. Okay? Now, rho of t, this good. But we still have these HIs that we have to integrate over time. So it's not Markovian, still not Markovian. But also we still have the total density matrix. So this has the dimension of the total system that we have. Okay? So let's start reducing the dimension. So the next step, I think is step 3. Partial trace. Now we know, this is basic classic mechanics, that if we have the total density matrix, the density matrix for our system will be just the trace over the environment of this total density matrix. Okay, this is well known. So what do we need to do if we want a master equation that depends only on the reduced density matrix of our system is to trace over the environment? We're going to get something like dot t is equal to minus I alpha trace over E of hi of t rho t 0 hat and hat. Here the hat I don't need, but okay. Minus alpha square integration between 0 and t of the trace over E of hi of t hi of s of t differential of s hat and hat and hat. Okay, and now we have to calculate this trace, and this is basically all we are going to do is to calculate this trace. Okay, and to see if we have to make any further assumption in order to be able to calculate. Once we calculate this trace, we are done, and we have our Redfield master equation. Okay, let's start with this. Okay, let's call it this first part. Okay, so now it's full calculation only of this part. Okay. Well, first of all, we need some expression at least for the interaction Hamilton. If we are going to trace, what is required to do is to separate this Hamiltonian in the part that affects to the system and the part that affects to the environment. Okay, this without any assumption, we can write that hi has this form. I times A. Okay, this does not require any assumption. Any Hamiltonian, you have two Hilbert spaces, you can separate in the part that affects the system, the part that affects the environment, but you have to sum over several of them to make this the composite. Okay, sometimes you get only one, S times E, but this is not linear. Okay, of course this happens the same in the interaction picture. Okay, because it's basically the same thing. So we are going to, we have to do the same with the system, with the total system, okay? And there comes another very, very strong assumption that we are going to make, okay? That is that, well, we can relax it a little bit, but then we will make it stronger later on. What we need at this point is to assume that at the initial time, both system and environment were uncorrelated, were separable. There is no entanglement between the system and the environment, okay? Is this a very strong assumption? It depends. If you have, for instance, a system that you move and you put it in contact with another system, you expect them not to have any correlation. But what this means is that you need your time series at very special time, because it's the time you put them in contact. Okay? If you have an atom interacting with the radiation field, it is expectable that there should be some correlations there, and you don't have this condition for a certain time. Or you assume, that is what we are going to assume later on, that this happens forever, that you don't get any entanglement between the system and the environment. But at this moment, it's only for the initial state. If you don't impose this, again, very complicated problem. Okay? You cannot get rid of this commutator here, and the problem gets very, very difficult. Okay? So these are the two main assumptions: weak coupling, separability at the initial time. Okay? If we assume these two, this commutator, that is what we want to calculate, we can write it like this way: sum over I, the trace of Si times Ei hat and hat rho S times 0 on the environment. This is just math. Okay, we have only thing we have assumed is here. Okay, because here we are summing up. Okay, so there is no assumption on the interaction Hamiltonian, only on the initial state. Okay, this we can just write how it is. Would be sum over I, trace over E of Si rho S. No, I'm writing rho S, but I say that rho S is rho. Okay, 0 minus rho of 0 Si, all of it. Let me take the trace inside. So this times the trace of Ei rho E 0. Okay, you see what I have done here, no? First, I expand the commutator, and then I take the trace all over it. And the trace of Ei rho E is the same as the trace of rho E Ei, because the permutation, the cyclic property of the trace. Okay, so I only get the commutator in the S part, because the other one is cyclic. Okay, and this is just some expectation value of this Ei value. Okay, at 0. These Eis are the operators of the interaction Hamiltonian acting on the environment. Okay? Then, at this point, many books, what they do is to say that these expectation values are 0. Okay? And they claim that this is because these are just some energy levels, and you can just shift the environment Hamiltonian however you want in order to make them equal to 0. Okay? I don't really see what is the reason behind that. Okay, I have found another way of documenting it, let's say, of justifying that we can take them equal to 0 independently of the interaction Hamiltonian. Basically, the idea is if you have this, the total Hamiltonian, I can just modify it in this way. The total Hamiltonian is the age of the system plus age of the environment plus alpha H interaction, and I can just add, what you see, I, SI, identity, multiplied by this one, EI, at 0. Okay, and alpha here. So I can just add this term with the price of removing it later on. Minus alpha, phi, SI, identity. Okay, I can add and remove whatever I want because this doesn't change anything. And what I'm going to do, to make it easier, here. First I subtract and then I add, and I'm going to call this HI prime. Okay? This is something I can do because I add and remove. Okay, so it's the same thing. And for this HI prime, SI times I minus you can write it this way. You take this SI as a common factor and you get the AI from the interaction Hamiltonian minus the identity with these guys. And then when you calculate for this new interaction Hamiltonian, this expectation value, you are ensured that you get them 0. Because if they were not different from 0 at the beginning, you just remove them all the way on. Okay? And the price that you pay is that you have this. But okay, as this is an operator only in the system Hilbert space, I just absorb it in the system Hamiltonian. Okay? I absorb it in the system Hamiltonian. This is where people say, and this does not affect the system Hamiltonian because it's just a shuffling of the energy levels. This I'm not so sure. You have to check for all possible system operators, what happens, and so on. But in any case, I don't care. I just change my system Hamiltonian by another system Hamiltonian, and I keep working because if I can solve the equation for one Hamiltonian, I can solve it for another Hamiltonian. So if I want to say that this doesn't matter, it doesn't matter. If it matters, okay, I get a new equation and I solve my new equation. Okay? So this is the reasoning, and you will see that it happens the same with the Limblad-Master equation. There is another term that you have to absorb, that is the lamp-shift Hamiltonian, that usually many books say that it doesn't matter because energy levels, but there are many people that say no, you have to prove that it doesn't matter for each problem that you have. Okay? But in any case, it's something manageable. It doesn't change the structure of our problem. Okay? So what we conclude is that this term here, number 1, is equal to 0. And we get only this part of the equation. Okay? Okay, let's work the second part of the equation. And now is where things get super fun, because we have to expand this double commutator. And this is where we can get super confused with the order and the sign and all the things that are super happy. Okay? Super fun. This, we say that is equal to 0, as we have proved. So this is the equation that we have right now. Okay? We are going to make another, this is a different step, let me check. No, still tracing. Okay, now if we want to move forward, we need to, well, this is already, I don't write it down because I don't like it, but this is already called usually Redfield equation, okay? Even if it is not Markovian. This is not Markovian because this depends on time. You have to integrate between 0 and time that you have, okay? The state of the system does not depend on time, okay? But as we have the state, because this is the state only in the interaction picture, okay? So we have some dependence in the Hamiltonian. You have still to make an integration through the whole path, and you don't forget, let's say, the state of the original state of the system, okay, the initial state. Okay, so let's make this a little more clear. Let's say instead of writing T and S, we don't like it. Let's use. Let's try to, of course, S goes from 0 to T. So let's try to measure how far are we from T. Okay, this is just a change that we are going to make. Let's define an S prime that is T minus S, for instance. Okay? Or let's say the other way around. No, it's the same thing. We were going to write S equal to T minus S prime, but it's the same equation. Okay? So then we can write this equation in this way. Okay, and when S is equal to 0, this is T. When S is equal to T, this is 0, so it will switch. So we just, instead of switching, we just have here a plus. That is also irrelevant. If you see in the books, usually this can come with a plus or with a minus because it also just depends on the structure of the Hamiltonian. So it's really not relevant. Okay, I think in Breuer and Pretuchonic's book, this is with minus, and then in Wikipedia is with plus. Okay, so it doesn't really matter. Okay, but let's do this way so we don't have to wear all the minus all the time. Okay, and as S is just a dummy variable, we just remove the prime, so we just keep with S. But the only thing that matters is that we change from S to T minus S. That is exactly the same because S goes from 0 to T. Okay, T minus S goes from 0 to T. This is just going the other way around. But this because it's more intuitive to see that here what we are measuring is how far are we from our state. Okay, we have to go far before or not. Okay, and now, sorry, this we take the trace over the environment to get the reduced equation of motion, and now we have to make another assumption. We are stuck again. This is very difficult to calculate. If we want to go further, we have to assume something from the state that I said before. We are going to assume that this is this is still rho total. Sorry, total is rho of the state. So we are assuming here. No, we need to assume that it is constant with time. Okay? You can also relax this assumption. Okay, let's relax it, but we need to make this assumption later on. Now, we can say just that it is separable at all times. Okay? Meaning that the system and the environment, they interact. Of course, is this a realistic assumption? It's not. Okay? If the system and the environment, they interact, some entanglement will be created, and you cannot always write it this time. But what we are assuming is that this entanglement reduces very fast or decays very fast, so the correlations between the system and the environment are not long-living, and this is something that we are going to assume later on. Okay, that we will fix this one. Okay, so basically what we want now is to assume that there are no strong correlations between the system and the environment. And this is also an assumption that is usually made in classical physics when you derive Markovian master equations. Okay? So we assume this. And as I say, now fun begins. because we can expand. What we are going to do is just to expand this commutator. Okay? And here, please be cautious, because we can make many mistakes, or I can make many mistakes. Integration between 0 and t. Let's write here differential of s, trace over e. No, not so big. And now we will have hi of t hat times hi t minus s times rho of t minus rho of t hi t minus s hat and hat and hat and hat. This will be term minus the same here, hi t minus s rho t minus rho t hi t minus s, and now this comes on the other hi of t hat 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 and hat. If I didn't make any mistake, this is what you get. Okay? If this is equal to this, then here and here. And now we multiply. So we get 4 terms. Integral of s, trace over e. Let's separate in traces, because the trace is additive. Trace of a plus b, trace of a plus trace of b. So we take this here, and now we get hi of t minus s rho t of t. Let's write it here now. Minus trace over e of hi of t rho t of t hi of t minus s hat and hat and hat minus trace of e of hi of t minus s, I'm here, rho t of t hat and hat hi of t. Plus, yeah, trace of over e of rho t of t hi of t minus s hi of t and close. Okay, if I haven't made any mistake, this is what we get. This is usually what is in the hats and hats. Hat, hat, and hat. Okay. Yes?
I did a plus in like for alpha. I think it's
This plus? Okay. This comes from changing the limits of integration. Okay? But I say it doesn't matter. In many books it is with a minus, in other books it's with a plus. You can just switch the interaction Hamiltonian, plus minus, and this is a phase, it doesn't matter, and then you get the same, okay? Okay, if there are no mistakes, this we have to be sure, because now we are keeping working. Now gets even funnier, more fun. Let's go here. Okay, because this we cannot work with this. What do we have to do now? Expand the hi of t, expand the hi of t minus s, expand the rho. Okay, so this will be equal to alpha. This is usually just a complaint. If you read any book, they say After very little algebra, you get to, okay, and this is the very little algebra, okay? I mean, it's not complicated, but it's cumbersome. It's a little boring to do, okay? Square, differential of S between 0 and t. Open this, and then we start with this guy here. Trace over E, and when we expand the HI, we are going to get, have it written, I have forgotten it, I have erased it, sorry. Let's write it here, okay? So you see, HI, remember, HI hat of T, that's the sum on I of SI of T times EI of T. Okay, this we have written almost at the beginning, okay? Remember that we are making the assumption that rho of T is equal to rho total of T is rho of T times rho environment of T. Okay? These are two things that we need to expand this equation. So, as we are going to get a summation here, let me just move it a little bit to the left. This will be alpha squared, summation. We are going to sum over I, but we have, you see, two interaction Hamiltonians in all the terms. So we have to sum over I, so over I prime, okay? I and I prime. Let's keep the notation that if it is T, we sum over I. If it is T minus S, we sum over I prime. Okay, but this is just notation. If you mix it, nothing happens. You are just multiplying terms, okay? So let's go. This will be A of Si of T, Si prime of T minus S, rho of T. Okay, so this is the part, yes, the part corresponding to the state here, no mistakes, product of EI of T, EI prime of T minus S, rho environment of T. Okay, I think I didn't make any mistake. Looks correct to me. And of course, hat and hat and hat and hat and hat and hat. Do you see what we are doing? We just take the part of the system to one side, the environment to the other one, and now this trace will come very naturally here. Okay? So this now minus trace over E of, now here we have HI of T, so it's SI, this I don't need, SI of T. Now what we have is the state in the middle, rho of T, Si prime of T minus S, hat and hat and hat, product, then should follow the same structure. I of T, rho E of T, E I prime of T minus S. Okay? You check. Trace over E. Now we have here, so we have first Si prime of T minus S. The state in the middle, rho of T. So then it should be Si of T. Like product of E I prime of T minus S. This S is a little curvy. The state, rho E of T, Si prime of T minus S. Environment. Plus, let's see, of now is the state, the first one, rho of T. Is HI of, so is I prime of T minus S, Si of T, times the state first of t hat. At this moment I start seeing everything the same. I think it's E prime of t minus s, E I of t hat. If I haven't made any mistake, okay?
I have a question
Yes.
about the third bracket.
Yes?
From the right, there are
Yes, there are two. Yeah, t minus s, t minus s,
and
t, and this. Yeah, no, thanks to you. Okay? Okay, are we happy? Now, the trace only applies here, okay? This will be, use another color, the trace of this here, okay? We will keep this, but the trace of this, we take the trace here, this is also a trace over the environment, of course. We also calculate the trace for this guy, and the trace for this other guy, trace over E, trace over E. Okay? No, I'm not going to write all down, okay? And these trace, what are them? Yes, this is the state, two operators, is an expectation value, what we call a correlation, okay? This trace will be equal to the expected value of AI t, AI prime of t minus s. Correct? Basically, if I measure these operators of the environment at the time t and at the time delayed with this t. Okay, what is the relation when I measure it at time t minus s and then I measure at time t? What are this correlation between them? Okay? And this is this guy, and this guy will be the same. This moves here because of the cyclic property of the trace. E I prime of t minus s, E I of t. Okay? Are we happy? This will be, I move this here because the cyclic property, so this will be equal to this one. And this one will be equal to this other one. This hat I no loss. Okay? So we get this, and then all the same. Okay? And this one, for instance, we are going to call C of t minus s. Okay? You can say, okay, it should be C of t and t minus s because it can change. Okay? Let's let it down here, but we are going to assume that it does not depend on time. Okay? This will be, as they are interchanged, is just C of t minus s complex conjugate. Okay? And this is again C of t minus s, and this is again the complex conjugate. Okay? Many algebra, but very simple. Okay? So now we can write the Redfield equation in the form that I think you are used to see. We need to erase from here. Point this that as I am very far, I won't see well. And we can take now that we understand it, we can take the last approximation we have to make. That is the Markovian approximation. Okay, it's here, because we need only this. So now we have rho hat t equal to alpha squared sum over I and I prime. Okay? Sorry, I have forgotten this C. T of this, of course, also C I prime because it depends on the indexes. Okay? I prime. Okay? We will see that sometimes what you assume is that you have only one term there, and this is also called the Redfield equation, okay? But in principle, the general one is like this. Integration or differential of s between 0 and t. And here we should mix the ones that are equal. So meaning this with this. Okay? This with this. Okay? Because they are the same, they depend on c of t. And if you see, is the commutator of, let me see. Maybe I make a mistake. It should be the commutator.
Because of the cyclic property, aren't the same the first and the
No, because the trace is over the environment. It doesn't affect the system operator. Okay? Let me mentally check. At this point, I'm already tired, so let me check. This is row S. This is S row. So what is the commutator is, let me check if I have it right or make be a mistake.
No, wait, because are you mapping the terms that have the same C, or are you mapping the terms that have C and C conjugate together? Because if you're mapping the terms that have C and C conjugate, then
But it should be the ones with the same C.
the same C.
It should be, but maybe I have mistaken C by C conjugate. Let's go over it, okay? Okay, this is SIT, prime, rho, okay? And this is EI prime, okay? That is what we call C. Then in this case, this is I and I prime. This I move here, so this is really the conjugate.
Yes. Okay.
And this is correct, I, normal, I prime, okay? And this is I prime, rho EI, this we move here, so this is equal to this, okay? And what I don't see is how to write this and this as a conjugator. It should be this. Yes, sorry. I just, it's a commutator, sorry. At this point, I get tired. This is like the commutator of is this I keep, this I keep, okay? And this is the commutator with, okay? So it's Si of t, commutator with the other one that is Si prime, t minus s, multiplied by rho of t hat by c of t minus s, I prime, okay? And all the other is just the Hermitian conjugate. Okay? You can see this is literally right, it's not so cumbersome. That you see that you get the opposite, and this you just have the complex conjugate. Okay? Basically, is that you choose I with I prime and t minus s with t. Okay? And this is what usually is called the Redfield equation, but there is still one more thing to do. We have this, we have done, it's all just algebra, okay, playing around with things, but if this, the original equation was not Markovian, this is still not Markovian. Why? Because we have the state depends on t, okay, but you have to integrate, because these are in the interaction picture, you have to integrate through the whole time, okay, so to make it Markovian, we need to make another assumption, okay? This assumption is that basically these expectation values that we have called like this sheet that we have called, Okay, these are correlations in the environment. Okay, you measure something in the environment, and then you wait for some time, and you measure it again. Okay, and if the environment is very big and the coupling is very weak, we can assume that these they are not zero, because if they are zero, you get no equation at all. Okay, it's like having no environment. But we are going to assume that they are close to zero when this gets bigger. Okay, so when you go away from the time that you are studying, okay, these correlations decay very fast. And because of that, we can change, for instance, this limit, alpha squared, sum of I prime, in 0 and infinity. Instead of S is I of t, is I prime of t minus S, rho of t, ci I prime of t minus S plus the Hermitian conjugate. Okay? Why to infinity? Because if this is going to be 0, it doesn't matter. Basically, what happens here is that this C, okay, if this is t minus S, they are very peaked around t minus S, and they go to 0. So for this, integrating between these two limits, or these two limits, or to infinity, it doesn't really matter. Okay? This, you can also take this instead of 0 to minus infinity if you want. It's not customary. Usually people don't do that, but you can. I mean, it doesn't matter. Because what we are saying is that the limits of the integration are not important. What is important is that here we have rho of t. Okay? And then it is Markovian in the sense that the time derivative of t depends not only on the state at t, but just in a small window of time around it. Okay? And this is what is usually called the Redfield equation. Okay? So this is the last equation. We finish here just some notes about the requirements. Have we gotten an equation that depends only on the state of the system? It's true. Okay, we have forgotten about the environment. The environment is hidden in these expectation values because it should be somewhere. It should have something. Usually, as I told before, it is also assumed sometimes that the environment doesn't change, and this makes this correlation function very easy to calculate. Okay, but it's not. You don't need. I mean, if you don't do so, you need to calculate the evolution of the environment, and then this becomes very, very complicated. But if you assume that this remains rho of t is rho total of t is rho of t times a fixed rho of the environment, this is just an integration that you have to calculate, okay? And this is not so complicated. If you don't make this assumption, more complicated, of course, okay? Is it Markovian? It is Markovian, okay? It is Markovian in the sense that you have only to look in a small window around your the time you are interested because of this approximation that we have made here. And I haven't said, this is called the Born-Markov approximation, the weak coupling plus this one. It's called Born-Markov approximation. Okay? Born-Markov. Okay? Does it preserve the trace? It does. And it's very easy to prove. You just take the trace, go tracing here, and you see that this no change of the trace. Basically, this like that. So you calculate the trace of this, and you get a 0. Okay? Meaning that the time derivative of the trace is equal to 0, so it doesn't change. Okay? This is very simple. It's not like when the book says simple and then it's a lot of calculation. Okay? But I have erased the other two requirements that we had, if you remember them. One is to be positive, meaning that the density matrix that you calculate through the evolution should be always positive, meaning that it always has positive eigenvalues, real and positive eigenvalues. The other one was to be completely positive. The Redfield equation is not, okay? It's not positive, and therefore it's not completely positive. This means that when you calculate it, when you calculate the time evolution, sometimes you can get negative eigenvalues, meaning that you are out of the physical regime that is only having positive eigenvalues, okay? And there are many ways to try to solve it with other more sophisticated master equations. And but what people usually do sometimes, well, usually I would say, they calculate the evolution, they calculate the eigenvalues of the density matrix every step of the evolution. And as soon as they don't get any of them negative, they trust the evolution. When they get one that is negative, they cut and they say, okay, they have gone too far in my evolution, okay? So this is basically all. In the next lecture, we derive the Lindblad master equation. That is, we impose that we want it to be completely positive. So then we have to make some other assumptions, like the rotating wave approximation. And we will transform this into a master equation that is much, much simpler. It doesn't involve integrating. Okay, it's super simple compared with this one, but it's also more restrictive regarding the assumptions that you make with the bus and the system interaction. And just mention that if you go to many references, you will find this equation without this summation. Okay, this is very common. This is just an assumption. If you assume that the that the interaction Hamiltonian have this form, okay? If you assume that there is only one operator in this expansion that you make into the system operator and the environment operator, then you can remove all these summations, okay? You just get only the I equal to 1 terms, and you have only one, okay? So without I, okay? Something like this. Also happens in many cases. If you have a system coupled to a thermal bath, you can model it with only one channel. That is how we call these operators, and then it is doable. Okay? Questions? Everything clear? So we finish here.